Alright, welcome to APNIC eLearning web class. Today we'll be doing OSPF Basics. So we'll be discussing about the basics of OSPF routing protocol, right? So I believe some of you heard about OSPF, some of you probably work with OSPF a little bit, okay? So what we'll be covering, just the basic of OSPF, what is OSPF, what type of routing protocol is OSPF, how OSPF operate, right? What are the topology types that OSPF supports? Yeah, all those sort of things. Okay, before we move forward, a little bit of introduction of myself. My name is Nurul Islam Roman. I am the Technical Training Officer now in APNIC. So I'm in APNIC since 2006. When I first joined in APNIC, I used to be the host master. So I deal with the IP address, AS number request that time. Then afterward, I move into the training team as a technical trainer to share my knowledge and experience that I have on IP network. I'm in the industry since since 1998 and working on IP core network. So yeah, as you can see on the slide, I'm specialized in routing switching, IPv6, DNS, DNSSEC, Internet Resource Management, network security, all sort of infrastructures related stuff. All right, so yeah, and also we have a support page, www.apnic.net/elearning support. If you face any difficulties in technical issues that you might face when you use this platform, it's worth having a look on this website, right? So that might solve some of your problem that you are facing. And after you finish the presentation today, we encourage you to spare some time and give us the feedback. So your feedback is very important for us because this is how we try to kind of improve our e-learning session in future and also cater your requirement or your need. All right, and lastly, on that slide, acknowledgement to Cisco systems, because it's a technical presentation and based on OSPF. So yeah, we used or we took help from Cisco to prepare this presentation in terms of using some of their materials, their books and all sort of things. All right, so let's move on. And also, when we'll be doing the presentation, if you have any question while I'll be presenting, just raise your hand and ask the question. Just type your question on the box or chat box. I'll try to pick up your question and try to answer as soon as I can. Okay, so yeah, you don't need to wait till the end of the presentation. If you have any question, just ask your question on the chat box. I'll try to answer it as quick as I can. All right, so let's move forward. OSPF, so open shortest path first. So this is what a routing protocol that's very popular now. This sort of routing protocol actually mostly used by the service provider. There's a link state routing protocol. So as you all know, routing protocol in terms of the way it works, we divide them into two category. One is distance vector, another one is link state. Distance vector is a very old one and link state is a very new one. The distance vector routing protocol, they actually propagate their whole routing table to the neighbors, right? And it has got some upside and some downside. Compared to that, OSPF or the link state routing protocol is the new one that actually overcomes some of the problem that distance vector has got, and it has got some downside as well in terms of bandwidth utilization, CPU utilization and all sort of things. But nowadays, link state is very popular. So we'll be classifying OSPF as a link state routing protocol in terms of the way it works. Link state routing protocol, which is OSPF as an example, or open shortest path first, that was developed by IETF, Internet Engineering Task Force, by the RFC 1247, and IETF, there is a working group called OSPF working group. They actually took the initiative and standardized the whole OSPF routing protocol. And this is how the vendors, for example, Cisco, Juniper, and others, right, they start developing their products. And when they all follow the RFC 1247, which is the IETF standard. Doesn't matter who are the manufacturer or who are the producer or who are the software developer, all works seamlessly. Okay. So now OSPF has got two versions, version 2 and version 3. Version 2 actually use to do routing for IP version 4 protocol, and version 3 used to do routing for IP version 6 protocol, right? So if you're having, or if you're running two protocol, IP version 4 and IP version 6 together, like call it dual stack at the same time. So in a dual stack machine, as a routing protocol, if you use OSPF, you need to use OSPF both version 2 and version 3. Okay. As you can see, version 2 has been standardized in RFC 2328 and version 3 has been standardized in RFC 2740. OSPF is basically designed for the TCP IP network environment, right? It's purely for IP. If you have other protocols, say IPS, XPX, AppleTalk, OSPF will not work. OSPF only works for IP. Why only work for IP? We'll explain later on. We have a slide. First, convergence. So OSPF, they converge very fast. What does that convergence means? Convergence is a time unit that will determine how fast, how quickly OSPF or the protocol will be able to start forwarding the packet, right? So if you see the routing protocol, the way it works, first, when you start the routing protocol on a router, it will start learning the topology. When it finish learning the whole topology, then it builds the routing table. When they finish building the routing table, then afterward it start forwarding the packet. So the convergence time is the point it start learning from there to the point it start forwarding the packet. This is the convergence time. So in OSPF, this convergence time is very fast. That can carry a variable length subnet mask. So if you have, or if you're using a variable length subnet mask in your network, select /25, /24, /26, /27 in different part of your network, or in different VLAN, you're using different subnets. OSPF can route all those variable length subnet masks. Some of the protocol, the old protocol, for example, RIP, the RIP version 1, version 2, and all sort of early protocol, they work on class full boundary. So they only can route class A, class B, and class C. All right. So OSPF can carry variable length subnet masks. It can carry discontiguous subnet, right? So you have a discontiguous subnet. So for example, /22 from one chunk of the IP block and /23 from the other chunk. It will work. It sends incremental updates. That's very important. So if there's any change happen on your network, only that update will be sent to the neighbors, not the whole table, not the whole topology, right? And it support route authentication for security. So it's a complete package. OSPF is a scalable protocol, and that runs on IP, and the protocol number of IP is 89. That is what I told you. OSPF can be work or can be useful for IP protocol, because if you see OSPF, the way it sends the control message, control information to the neighbors, right, all work on IP, right? So since the control information was sent on IP, so there is a dependency on IP for OSPF. So OSPF will not work any other protocol than IP, either for IP version 4 and version 6. For IP version 4, you need OSPF version 2, and IP version 6, you need OSPF version 3. Okay. All right, so let's move on. This is what sort of a schematic diagram of a link state routing protocol. We'll just try to give you a visual idea what link state routing protocol is. If you see the topology, there are a number of links, right, that you have in different routers. We have router Q, Z, Y, and X. So in all those routers, there are networks connected in a certain fashion, certain style. Each network has got their own prefix, own path cost, and all sort of other things. So when we use link state routing protocol, what they do, each routing table, they maintain their own topology table, topology database. And if you see within one OSPF instance, like OSPF protocol, all those routers, so for example in this case all those 4 routers, they share the same topology database. Same topology database they share, right? From that topology database, then each routing protocol, they use their own SPF algorithm or shortest path first algorithm to select the best path with reference to that particular router. Say, even though the topology table is identical to all four routers, but different routers, when they select the best path to the different destination, they select the best path putting them on the reference point, top of the reference point, right? So this is how each routing protocol will give best route that relates to that particular router. So for example, to destination, so for example, in this topology, if you see this destination in here from Q, right, router Q, the best path can be this, right? But from Z, the best path can be different. So that is why topology table can be identical, but routing table could be different depending on the best path from that particular router. Okay. So the bottom line is, in an OSPF instance, all router they share the same topology database, but when they calculate the best path, they use SPF algorithm. Each router will use their own SPF algorithm and they select their own best path, so that the routing table, if you see different routers, could be different, but topology table will be identical. Make sense? Okay, what is link state routing? Simple as that. They do not send full routing table on periodic interval. That's what distance vector routing protocol does. They do not send the full routing table in a periodic interval to their neighbor. So the disadvantage of this sort of routing is, if you send your full routing table to your neighbor, then your neighbor routing table will be influenced by you, right? So that's what we sometimes call routing by rumor. If you send the whole routing table, that's what distance vector does. But in OSPF or the link state routing protocol, they do not send the full routing table to their neighbor in a periodic interval. Okay, they maintain three tables. Link state routing protocol, they always maintain three tables. Number one is our neighbor table, right? So the table contains all those list of the neighbors. Then the topology table. The table contains the routing information, optimal path, suboptimal path, everything. Then the routing table that contain all those optimal path. When the optimal path goes to the routing table from the topology table, still topology table contain those all suboptimal path. Why? Because if the best path at that particular time goes down, then the second best path, which is the alternate path available in the topology table, will come up and install on the routing table. Okay, so this is how link state works. So they use shortest path first algorithm. So each router, as I said, use the shortest path first or SPF algorithm to select the best path from the topology table. Then they send a very small periodic update called hello message, which is very tiny packet, right? In periodic interval to their link. This is how they maintain their link state. So how it works? Say for example, router 1 and router 2, if they're connected, right, we call them neighbors, right? We'll see how they build up neighbor relationship. When it's been built, they learn the topology table, and then afterward they build the routing table, start forwarding the packet. At some point of time, if the link goes down, how router 1 will identify the link is down? Because there is a control information which is called hello packet sent every every certain interval. It depends on the topology. Normally Ethernet link is 10 seconds. So this is how the router will identify the link is down, right? Okay, so that's how they send the periodic hello message to maintain the link condition. Then also they send the trigger update. So if any network goes down on any of the routers and that router is participating on OSPF, they send the trigger update to the neighbors and let them know the network is down, so that the neighboring router don't need to wait till the next hello interval. They will know the link is down instantaneously, right? So that's what we call trigger update. So this is how the link state routing protocol works. Link state data structure. So in the link state routing protocol, how they maintain their data structure. So as I said, they maintain a neighbor table, they maintain a topology table, and then afterward they build the routing table. In the neighbor table, what they contain? They contain the list of all those neighbors, right? So when all the routers are physically connected, they start exchanging the hello message. By exchanging hello message, they discover the neighbor. Sometimes you have to configure a neighbor manually, but I'll discuss these things later on. But most of the case, OSPF discover a neighbor automatically. When the neighbor has been discovered, those neighbors list will come up on the neighbor table, right? And from this neighbor, those OSPF routers, they start learning their topology table. When the topology table has been learned, then they build the routing table. So this whole process we call, this is what the time they require to start learning, from start learning to forwarding packet. And this is what we call convergence time, as I have explained before. So to summarize, in a link state database, they maintain 3 table, topology table, most of the case that has been automatically learned. Then the neighbor table, most of the case that has been automatically learned, and then the topology table, right? So among the neighbors, they exchange the topology information, and they build up the neighbor table. Build up the topology table. Then afterward, they use SPF algorithm, and by using SPF algorithm from the topology table, they build the routing table. Okay. So this is what an example how SPF algorithm works. As I said, in an OSPF instance, every router, they share the same topology table. This is what a topology table for all those routers. In here we have router X, A, B, and all sort of all the routers, like each point is a router. So every router, they share the same topology table. Now if you see SPF tree, SPF path calculation, how SPF path calculation works, it's just an example. So for example, in this diagram, each path has got an equal cost of 10, right? Each path has got equal cost of 10. So now from X, if I need to go to F, right? How many path I have? Path I have X, A, D, F, X, D, F, X, C, D, F, X, E, D, X, C, E, G, D, F. So there's so many paths we have. If you see the path cost, say for example X to F, if I take this path cost is 10 plus 10, 20. From here to go to here, another path 10, 10, 20 plus 10, 30, 10, 10, 20, 30, 40. So many path costs. So if you see, when they build their best path or routing table, what they do, they put them on top of the tree, and from there they build all the branch of the tree, and each branch they have the path cost associated, and they add up the path cost, and this is how they select the best path. Okay, so bottom line, when any routers they start building their routing table or select the best path, they put them on top of the SPF tree, and from there they try to calculate all the available path to the destination and accumulated path cost, and based on the lowest path cost they select the best path. Make sense? All right, so let's move on. Some benefit or advantage of link state routing protocol: low bandwidth utilization. So when OSPF they maintain the link, they always utilize very less bandwidth from the link, so that all available bandwidth of that link can be used to forward the data traffic. Make sense? Okay. How achieve that? They only send the changes. So when the topology table has been built, routers are in convergence, then afterward when they maintain the table, what they do, if there's any change happen, only the change they send as a trigger update to the neighbors. So when the change will happen, then they will update the neighbors, and they send multicast for that, not broadcast. Since they send the multicast, so only the member of the group, OSPF group, will receive the update packet, right? In most of the case, if it's a point-to-point link, on that link only 2 neighbor, right? So that's why very less bandwidth utilization. Even on the LAN, if you have 3-4 routers connected, they select the DR and BDR, and they send multicast to the DR, and from there DR propagated to the other route. I'll show you, there's a slide. So on that slide, OSPF use multicast. Since they use multicast, single packet can be copied to all the members. So all those OSPF participating routers, they don't need to generate individual packet to the individual neighbor. Just one packet that can be replicated to the other participating neighbor. Make sense? Okay. First, convergence. So since I have already explained, each router, when they finish learning their topology table, and from there they build their routing table, and then afterward, if the primary path goes down, right, then there's alternative path on the topology table. Quickly that alternate path will come and install into the routing table. So that's how OSPF ensure fastest convergence. So they detect the link failure by using a trigger update. When the trigger update comes, they quickly run the topology table again on the they quickly run the SPF algorithm on the topology table, and from there they select the best path. So this is how they ensure the faster convergence in topology changes. That's sort of an example how the alternate path can come into the routing table very quickly. So another example of how they find the new route. So when the network change happen, right? When the network change happen, the router who identify the change, they send a trigger update by an LSA or link state advertisement to all participating routers or the neighboring routers. When that goes to the neighboring routers, the neighboring routers, they identify, yes, there is a change happen on the network. Even though the router is remote, like from R1 it connects to R3 in here, the topology change happen on R1 link, right? So R3, how they know that? Because R1 send the trigger update, right? So this is how they quickly know, R3 quickly know there is a network change happen, and they quickly can run SPF algorithm into the topology table and find out an alternate path. So this is how they ensure the faster convergence in the network change. So let's have a look the basic operation of OSPF, how OSPF operate. There are some stages. First, the neighbor discovery. When you configure a OSPF routing protocol on any of the router, first job is to discover the neighbor. So to discover the neighbor, most of the case, what router does, they send a layer 3 multicast message or layer 3 hello message to their connected routers or connected links. So which are the links are activated for OSPF? On those links, they will send a hello message, and that is on multicast. When that hello message goes to the neighbors, so if the neighbor also listening to that OSPF multicast address, when they listen to multicast address, when you configure OSPF on that router as well, right, and on that link, so then they will send kind of an acknowledgement for the hello, and this is how they build a neighbor relationship. When the neighbor relationship has been built, then they start exchanging the topology table. We call it LSDB or link state database. That is also sent on layer 3 multicast message. So all the topology table they send on the multicast. So the advantage of multicasting is the router who is sending the topology table, even though they have 10-15 neighbors, he only need to create one packet. On the packet, source is his router ID and destination is the multicast group address. We'll explain what will be the multicast group address. Then the topology table goes to all the routers within the OSPF instance or OSPF process, and then afterward they use the SPF algorithm to select the best path. As I said, the topology table will be identical across all the routers within the area, right? And then afterward, they build the routing table by using the SPF algorithm. Okay, now we'll see all those stages in very detail. So this is what the topology. Those 3 routers are connected to a switch. We call it a LAN type of network, or in terms of OSPF language, broadcast multi-access network, right? In the sort of topology, how it works, all those routers, all 3 routers, when you configure OSPF and activated that interfaces for OSPF, they start Initially they're at the downstage, right? And then when you configure OSPF, right, they send a multicast message. So on the packet source is their address, and then packet destination is this multicast group for IPv4, that multicast group for IPv6, 224.0.0.5 or FM02::5 for IPv6. So if this is the multicast group address, then that multicast packet will go to the network, and this is how it will go to all the routers, the multicast message. So this stage, when those routers send that multicast hello message across the link, we call it initialization stage or init stage. So router is trying to initialize their neighbor. Then afterward, all the neighboring router with OSPF enable, they receive the hello packet. When they receive the hello packet, what they do, they check the content of the hello message, what I received on the hello message, right? And after I receive, what are the information that already included on the hello message match with its own information. I'll explain, there is a slide, information, right? Then they build a relationship we call OSPF two-way relationship. What are the information need to match? Here is the slide. In the hello, those messages will be included. Out of all those messages, those star mark messages like hello and date interval, area ID, and any authentication information if there is any, those three must match. When all those match, then they will build a neighbor relationship. We call it two-way stage, not a neighbor relationship yet, two-way stage. So when they build the two-way stage, then they will decide, okay, now we need to exchange our summary database table, right? So who will start exchanging first? Because if all of them start together, there will be a chaos, right, on the network. So they decide who will start first. Okay, who has got the highest router ID among all those neighbors? They will start first. So who is the highest router ID? He will start sending his hello database, summary database. So when they decide who will send first, we call it X start stage, right? At X start stage, they decided, and then the highest router ID, he will start exchanging the summary table, database table or topology table. That's what we call exchange state, right? At the exchange state, all the routers, they receive the summary, and what they do, they check what they receive and they check what they have, right? So, and then when they check what they have and what they receive, if there is the same topology information, same network information, and there is a field on that database called link ID or link numbers, right? So if that match, then what they do, if the sequence number that they receive is higher than or the latest, then they already have what they do. Just a sec. The sequence number they have higher than what they receive, they just discard it and they send the latest one back to the sending neighbor. And other way around, if what they receive has got highest sequence number than what they have, then they override that into their topology table, right? And if they don't have any, what they receive, they ask for the full information. Okay, let's send us the full information on that particular network updates. So when that comes, they build their topology table. This is what we call full stage. At the full stage, they synchronize their whole topology table. Okay, that is what the sequence number, how they maintain. How they maintain the routing information. First, as I said, they send periodic hello message. For the LAN type of network, this is 10 second, right? So they change hello message every 10 second, and then they send trigger update if there is any network change happen on the network, if there is a topology change happen on the network, right? And then afterward, they maintain their link stage or the routing information with the sequence number. Sequence number is a 32-bit number or 4-byte number, right? So every LSA that comes will be associated with a sequence number. So when they receive any LSA from the neighbor, they always try to check into their database what sequence number they have on that existing one and what sequence number they have on the receiving one. If they match the same, they just discard it. If the receiving one is the highest sequence number, then what we have or the router have, they override it. If the receiving one is the old one or the low one number, then what it has got already on the database, they send or they discard that and they send that latest one from the topology table back to the sending neighbor. So this is how they maintain their routing information. Okay, makes sense? Any questions so far? What we discussed? So as I said, if you have any question, you can ask me that question anytime. You don't need to wait till the end of the presentation. Okay. All right. Now we'll explain OSPF packet type. What type of packet that OSPF has got? OSPF use 5 packet type, right? When they kind of exchange routing information, they maintain routing information, and they build routing table. So number 1 is OSPF packet type 1, and that is what hello message, which is sent every 10 seconds. So usually hello message, they build adjacencies or neighbor relationship between neighbors. Okay. Number 2 packet is database descriptor packet or DBD. That database descriptor packet usually contain the topology information or network information. Then LSR packet or link state request packet. What is the link state request packet and why it is used for? If any router has got any packet forwarding request to a destination and that destination is not available on the routing table or even in the topology table, what the router does, before router discard the packet, it asks the neighbor by using LSR, link state request, do you have any information for that particular network? If the no reply comes back, they discard it. If the reply comes with information, then this is how they build the table, routing table, and forward the packet to that destination. Then 4th one is link state update. Link state updates. So what is the link state update? Link state update is any change happen on the network or any kind of LSR request comes from downstream routers, right? They send those reply using link state update packet. Then afterward, the last one is link state acknowledgement or LS acknowledgement. That type of packet, link state acknowledgement, actually used to acknowledge for every link state update or link state request that it received, right? Why they use the acknowledgement? Because this is how they ensure the reliability. As I said, OSPF use IP, right, to exchange control information. So IP usually a datagram, it doesn't have any acknowledgement. IP doesn't have any inbuilt acknowledgement mechanism. That is why OSPF, they created a special packet called link state acknowledgement packet. By using link state acknowledgement packet, even though OSPF use a datagram, IP datagram, but still it has got acknowledgement because OSPF has got their own special acknowledgement packet. Make sense? Okay. Let's have a look the format of an OSPF packet, how the OSPF packet look like. All those 5 OSPF packet that we saw actually will be included in this OSPF packet format. So this is what the format of the packet. So let's have a look. This OSPF packet, obviously it has got the link header, which is called layer 2 header. Then afterward it has got IP header. On that IP header, the OSPF participating router, they use their router ID as a source, and they use as a destination, they use the multicast address. If it is IPv4, they use 224.0.0.5. If it's IPv6, FF02::5, right? And then afterward, we have OSPF packet. Within OSPF packet, those are the information are included. And they have got their version number, type, packet length, router ID, area ID, checksums, and all sort of information that we saw in the previous slide, right? So now the question is, okay, What's the difference between OSPF version 2 and version 3? Right? On the packet type, almost similar, and the change is on here IP packet header or IP header. So between version 2 and version 3, OSPF packet type, if you see inside, not much change. Little bit change, but there is no big change on the architecture of OSPF. Okay. So what the change they did on OSPF version 3, they use a 32-bit address as a router ID. Still 32-bit address as a router ID. On the IPv6 header, source and destination packet address are different in here, but on the OSPF router ID, still they use a 32-bit address. All right, let's move on. So those are the header field that we have within OSPF: packet, version number, packet type, packet length, router ID, right? As I said, this router ID is 32-bit for both IPv4 and IPv6. If you are running an IPv6 only machine, you need to use any 32-bit address as a router ID by using router ID command, right? And then area ID, checksum, and authentication all are same. Okay. Content of OSPF packet data. So for hello packet, that contain the list of all those neighbors. So when you are sending hello packet, the data part of the OSPF packet, they will contain the list of all OSPF neighbors. For DVD packet, that contain the summary of the LSDB. So link state database summary will be on the DVD packet, and that includes all known router ID and their sequence number, obviously the latest sequence number. For link state requests, that contain the router ID of the router who is asking for the link state request, right? For link state update, the full LSA ID will be contained on the data packet for link state update, right? And acknowledgement packet, for the acknowledgement, the data part is all empty. Only the header will be sent. Make sense? This is how the packet has been structured for OSPF. If you have a look, the difference between OSPF version 3 and version 2, as I said, only on the IP header, source address and destination address will be changed. But on the OSPF packet, same exactly, a little bit changed probably, right, in terms of new LSS that has been introduced in OSPF version 3. But router ID and all will be same. Okay. Now we'll discuss about the OSPF network topologies. So what is OSPF network topology, right? So as we can see, if we build an OSPF network, right, it can be built in different type of topology. It can be a point-to-point network, so like, through using WAN interface or serial interface of router, two routers are internally connected. That's what we call point-to-point network, right? Or it can be an Ethernet network where number of routers are connected, or it can be an X25 or frame relay network. So different topology that has got. So depending on the topology that has been used to build OSPF network, the neighbor relationship or the way OSPF works to build neighbor relationship will be different, right? So that is why topology is very important to learn OSPF or to understand in OSPF. Let's look what are the topology that OSPF supports. OSPF basically supports three type of topology. Broadcast multi-access, which is the LAN type of network where all those routers share the same Ethernet link. The second one can be a point-to-point network. On a point-to-point network, as I said, two routers are connected on a serial interface of a router. Or the third one is non-broadcast multi-access, NBMA, right? It means in all those routers, they're connected to a WAN service provider. They're providing frame relay, ATM or X25 service, and broadcasts are not allowed on this link, right? Since broadcasts are not allowed on this link, so on the link layer 2, then how the multicast frame will be forwarded to all those group members. So that's why neighbor relationship for different topology will be different. Let's explain In a broadcast and multi-access network, how OSPF build neighbor relationship. Okay, generally Ethernet or token ring type of network we call broadcast multi-access. So in this type of topology, there is a possibility if all those OSPF neighbors, they start building up neighbor relationship with other neighbors and they start exchanging the topology information, there will be a lot of control information will be exchanged on the link, right? That's a sort of a wastage of link bandwidth. So in this sort of topology, to bring a discipline, right, into OSPF control information, how that will be exchanged, they first elect a DR or a designated router and a BDR or backup designated router. What is this? It means in this diagram, among all those 5 routers, one router will be elected as a DR or designated router. So he's kind of a leader of the OSPF link. So every router, when they need to send information, instead of sending to everyone, they all send it to the DR or designated router. And DR or designated router, they will forward it back to the others, right? So that is what sort of a central speaker that we have, and we all speak to the speaker, and speaker will propagate the message with other routers. Then BDR, which is backup designated router. Backup designated means if the DR is down for some reason, right, then the BDR will take the role and they start exchanging or propagating the message to the others. So in a broadcast multi-access network, the way they build the neighbor relationship, they build or they elect the DR first, and then they elect the BDR, and when the message will be sent, they all send the message to the DR. And when they send the message to the DR, there is a special multicast address for that, which is 224.0.0.6 for IPv4 and FF02::6 for IPv6. So this is what the multicast message for the DR. When it goes to the DR, reply comes back. When the reply comes back, that actually sent to the multicast address, which is FF02::5 for IPv6, 224.0.0.5 for IPv6, v4. Default OSPF hello is 10 seconds in the broadcast multi-access network, and data interface is 4 times of the hello, which is 40 seconds. So this is what the behavior or the neighbor relationship behavior for broadcast multi-access network. Okay, so when they select or they elect the DR in the broadcast multi-access network, how they elect the DR? They look at the priority of those routers, right? If all the router has got the same priority, then they check the highest router ID. Who has got the highest router ID? They will be the DR, right? Highest router ID in terms of IP address, IPv4 or v6. They will become the DR. Second highest will be BDR. And as I said, when the packet goes to DR, it will be sent to 224.0.0.6 for IPv4, FF02::6 for IPv6. When DR send the message back to the others, they send the message to 224.0.0.5 for IPv4, FF02::5 for IPv6, right? So all the neighbors, when all the routers they build the neighbor relationship with DR, it will obviously be a full adjacency, right? DR and BDR, right? And with other routers within the link, without DR and BDR, the relationship will be a two-way relationship, right? Two-way relationship. They only exchange the hello message, that's it. They don't exchange any database message or database information. They always exchange the database information with the DR and BDR. As I said, BDR election process, if the priorities are same, they will use the highest router ID to select the DR. How you can manipulate the DR? Because within the topology, if we want a certain router to be DR, how you can do that? Either you can change the priority of the router, right? Or you can install a highest IP address on the router ID. That's how you can manipulate it. Okay, the second topology that we have, point to point. So usually two routers are connected back to back like this using serial link. So in this sort of topology, normally we use HDLC or PPP encapsulation on layer 2, right? So this point-to-point network, they don't need to select any DR and BDR because only 2 routers. So they build a neighbor relationship which is full OSPF neighbor relationship, and they exchange hello 10 seconds and their interval is 40 seconds. Then the third one is non-broadcast multi-access network. What is non-broadcast multi-access network, or NBMA? So this is a type of topology that we have. So for example, X25, frame relay and ATM, they are non-broadcast multi-access. What does that mean, non-broadcast multi-access? It means in here we have our WAN service provider cloud, right? This is what our WAN service provider cloud. So when you need to connect 2 or 3 sites, what you do, the WAN service provider, they will connect you to the nearest exchange. When they will connect you to the nearest exchange, they will build a virtual circuit in between those sites, right? So when you need to send any packet from one side to the other side, the packet on the layer 2, when frame will be created, will be forwarded via that virtual circuit. So if you connect another link here, so that packet cannot be forwarded to the other side. So if you need to forward that packet or the frame to the other side, you need to use other virtual circuit from this router for that. So that's why it is a non-broadcast multi-access network. So in this sort of topology, when OSPF send the multicast message, the multicast message no way will be forwarded to the all other members, because when the multicast message will be forwarded, it will use only the particular virtual circuit and it will be reached to the particular destination on the other side, not all machines, even though it's a multicast or broadcast. So that is why in this non-broadcast multi-access type of topology, say for example X25 network, the legacy frame relay network, still we can see some frame relay networks available. ATM, there is a requirement of building the DR and BDR by a manual configuration. So we cannot discover DR and BDR automatically. We need to configure DR and BDR manually, and all the neighbor relationship manually. So how we do that? So for example, when you configure OSPF in a frame relay or X25 or ATM network, you need to manually configure your neighbor by using a neighbor's relationship statement, right? So when you did that on the both sides, then you will see they build up a neighbor relationship. So when they build a neighbor relationship, then afterward they can start exchanging all the hello and then database information. So yeah, so they cannot discover neighbor automatically. And in the frame relay network or the non-broadcast multi-access network, the default hello interval is 30 seconds, whereas on the other 2 topology it was 10 seconds, and dead interval is 4 times of hello, which is 120 seconds. Make sense? So yeah, so those are the 3 topology that OSPF supports. Okay, now we are at the end of the presentation today. So we can take some questions because we have some times to take your question. Also, if you need to kind of download the presentation slide, so what we suggest, you just go to that URL, finish the feedback. When you finish the feedback, that will take you to that FTP site. From that FTP site, you can download the presentation that we used today. Okay. So yeah, so that's what the end of the presentation today. Is there any questions so far from the participants? You have 5 minutes, for the question and answer. So if not, then to sum it up, so if you need further help, so for example, if you have any question, you can come to APNIC Helpdesk. So when you come to APNIC Helpdesk, there is a website www.apnic.net, and then go to services. It will take you to a page. From there you can come to APNIC Helpdesk chat, right? So on the chat, there is a link in here. Say if you click, you will have a person to help you. And our help desk that runs from 9 AM to 9 PM in Brisbane time. So Brisbane time is GMT +10. So you can talk to help desk staff if you have any question, or if you have any particular question related to training or OSPF or the presentation that we did, you can send an email to training@apnic.net and we'll try to answer your question. Okay, so I hope this presentation will be useful for you, and if you need to attend any of the future e-learning web class, we have a schedule that runs on our website. If you go to www.apnic.net/training, then you can see all those e-learning sessions that we have upcoming, a future e-learning session. Just register for any of the e-learning session and make yourself available at that particular time. You can attend our e-learning web class. Okay, so thank you very much, and hope we will see you in any of the future event.